Just 72 hours prior, the European Space Agency unveiled what they described as the most intimate perspective yet of 3 Atlas, the celestial visitor that has simultaneously enthralled and unnerved the globe. Billions were invested in cutting-edge space technology, and 7 Martian orbiters were strategically positioned to capture this once-in-a-lifetime vista. And what was the result? A hazy white speck, resembling nothing more than a smudged lens. Within moments, social media ignited, not with awe, but with indignation. Amateur stargazers, armed with their backyard telescopes, were documenting clearer images of comets residing millions of miles further away. Yet, NASA, with its Mars Reconnaissance Orbiter boasting the most potent camera ever dispatched to another planet, has remained conspicuously silent. The explanation of a government shutdown is wearing increasingly thin, particularly when one considers the parallel, unexplained quietude from Chinese and UAE orbiters. By the time you conclude this broadcast, 3i Atlas will be less than a week from vanishing behind the sun, obscured from every terrestrial telescope during what should be its most spectacular phase. And if Harvard physicist Avi Lowe's assertions hold true, the events that follow could fundamentally alter our understanding of the possibilities within our cosmic vicinity. If this enigma captivates you as much as it does me, please engage the like button and subscribe to remain informed as this narrative unfolds in real time. Share in the comments your location, the current time there, and whether you believe we are being furnished with the unvarnished truth regarding 3i Atlas. Furthermore, to aid in the expansion of our community, I encourage you to share this with your networks on X, Facebook, Reddit, or your preferred messaging application. Your consistent support is deeply appreciated. Chapter 1. The photographic debut that rocked the internet. The 7th and 8th of October 2025 will be etched in memory as the moment the space exploration community collectively surrendered its patience. For months, anticipation had been building. 3 Atlas, a mere 3rd confirmed interstellar object to traverse our solar system, was approaching its closest point to Mars. 7 distinct spacecraft from 4 separate space agencies were poised to capture groundbreaking imagery. The excitement was palpable. Scientists had promised us clarity, definitive answers, perhaps even irrefutable proof of its true nature. And then the images were released. The European Space Agency's ExoMars Trace Gas Orbiter, positioned a mere 30 million kilometers from 3i Atlas during its closest approach on the 3rd of October, disseminated a series of images that can only be characterized as profoundly disappointing. A nebulous white dot, meandering slowly across a backdrop of stars. Devoid of detail, lacking discernible structure, offering absolutely no insight into whether we were observing a naturally occurring comet or something far more extraordinary. The public reaction was swift and scathing. Astronomy Vibes, a prominent space commentary platform on X, posted a side-by-side comparison that rapidly achieved viral status. On one panel, a sharp, highly detailed image of Comet Lemon, captured by an amateur astrophotographer using a standard mirrorless camera. On the opposing panel, the ESA's image of 3 Atlas. The accompanying text queried, "If a simple mirrorless camera can capture Comet Lemon, why can't NASA photograph 3i Atlas as it passes near Mars?" The post has since garnered over 40,000 reposts and continues to climb. However, it was the subsequent commentary that truly resonated. Billions in funding, and this is their most impressive photograph. It bears a greater resemblance to a weather balloon adrift in a misty backyard. To fully grasp the depth of public ire, one must comprehend the contrast between expectations and reality. The Cassie camera aboard the ExoMars Trace Gas Orbiter possesses an angular resolution of 11.36 microradians per pixel. At a distance of 30 million kilometers, this translates to 340 kilometers per pixel. For context, the estimated nucleus of 3i Atlas measures between 5 and 46 kilometers across. This implies that the entire solid core of this object would, at best occupy a minute fraction of a single pixel within these captured images. However, the situation becomes even more intriguing. The ESA was fully cognizant of these limitations beforehand. They were aware that their cameras were engineered to photograph the luminous Martian surface from a proximity of only a few hundred kilometers, not faint celestial bodies situated tens of millions of kilometers away. Nick Thomas, the lead investigator for the Cassie camera, acknowledged this reality in their official statement, noting, "This was an exceptionally demanding observation for the instrument. The comet is approximately 10,000 to 100,000 times fainter than our typical targets. So, why release imagery they knew would be insufficient? Why cultivate anticipation for months, only to deliver something that provides no new informational value? The official narrative suggests they presented the available data, representing the apex of what their equipment could achieve. Yet, the timing feels calculated, almost as a deliberate release of pressure. Offer the public something, anything, to scrutinize while the truly significant data remains concealed. Because make no mistake, superior images, far superior images, exist, and they are being withheld." Chapter 2. The Elusive Crown Jewel. While the ESA was circulating indistinct specks, NASA's Mars Reconnaissance Orbiter was capturing something entirely distinct. The HiRISE camera, an acronym for High Resolution Imaging Science Experiment, stands as the most sophisticated camera ever sent to another planet. Its resolution is so precise that, from Martian orbit, it can discern objects as small as a kitchen table on the planetary surface. When 3i Atlas made its closest approach to Mars on the 3rd of October, HiRISE was operating with a resolution of approximately 30 kilometers per pixel, relative to the object's distance. This represents more than 10 times the capability of the ESA cameras. Should any structural intricacies, unusual formations, or deviations from the natural comet paradigm exist, HiRISE would have undoubtedly detected them. Avi Loeb, the Harvard physicist who has been meticulously tracking 3i Atlas since its discovery, articulated this point unequivocally in his most recent blog post. The brightest pixel in the HiRISE image will provide the most stringent constraint yet on the surface area of 3i Atlas. We are all eagerly anticipating the HiRISE team's swift release of their imagery. This statement was published on October 7th. It is now October 8th, and still nothing has materialized. The official explanation cites the ongoing United States government shutdown. Over 15,000 NASA employees, exceeding 80% of the agency's workforce, have been furloughed. The agency's website is not being updated and public communications have effectively ceased. It is a scenario of bureaucratic paralysis occurring at the most inopportune moment. However, herein lies the anomaly. The ESA, a European entity entirely unaffected by American political turmoil, managed to release its images. Similarly, China's Tianwen-1 orbiter, equipped with a moderate-resolution imaging camera, was also positioned to observe 3i Atlas. Its response? Utter silence. The UAE's Hope orbiter, outfitted with the Emirates Exploration Imager, also had an unobstructed view. And yet, nothing. Multiple space agencies, multiple sovereign nations with entirely independent bureaucratic structures and distinct priorities are all simultaneously incapable of, or unwilling to, disclose their most compelling data concerning the most scientifically significant object to visit our solar system in years. The pattern is difficult to dismiss. Social media is rife with conjecture. Some propose a coordinated effort. Others suggest that something remarkable was observed, necessitating meticulous review before public dissemination. The more conspiracy-minded posit that the imagery depicts something so anomalous that its release, without appropriate context, would incite widespread panic. This latter theory, while seemingly outlandish, gains traction when considering the events of the past week involving amateur observations. For while the official space agencies have been reticent with their data, backyard astronomers have been producing images that generate more questions than they resolve. Chapter 3. when amateurs observe what professionals conceal. On the 3rd of October, the very day 3 Atlas achieved its closest proximity to Mars, a Portuguese amateur astronomer, operating under the online pseudonym Dobsonian Power, uploaded an image that immediately went viral. Utilizing nothing more than a solar telescope from his own backyard and applying aggressive digital enhancement techniques, he captured what appears to be a distinctly angular structure within 3I Atlas. These are dark, geometric shapes, protrusions that bear no resemblance to the diffuse glow typically associated with a comet's coma. The caption he provided was concise, yet laden with profound implications. What on earth is it? Within a mere 6 hours, the image had been disseminated across every major astronomy forum, subreddit, and social media platform. The public response bifurcated almost instantaneously into 2 distinct camps. One faction perceived it as unequivocal evidence of artificial structures, proof that 3 Atlas is not what mainstream science purports it to be. The other faction dismissed it as a classic instance of pareidolia, the inherent human tendency to discern patterns in the absence of actual ones, exacerbated by processing artifacts stemming from unsuitable equipment. The debunkers presented robust technical arguments. Solar telescopes employ specialized filters designed to observe the sun's intense luminosity, not faint deep space objects hurtling at interstellar velocities. The equipment was simply not engineered for such observational tasks. When coupled with aggressive digital enhancement to compensate for the inadequate setup, the process essentially compels an algorithm to fabricate details that are not genuinely present. It is the astronomical equivalent of magnifying a blurred photograph to the point where one begins to perceive faces within the random noise. However, this is where the narrative becomes more intricate. Dobsonian Power is not some obscure internet provocateur with a rudimentary telescope and an overactive imagination. He is a respected amateur astronomer who has been consistently sharing authentic astrophotographic work for over a decade. His YouTube channel features meticulous documentation of his equipment, his methodologies, and his image processing workflows. This is not an individual attempting to fabricate evidence for fleeting online attention. Moreover, when questioned about the anomalous structures in his 3 Atlas image, he did not engage in unsubstantiated pronouncements. Instead, he readily admitted to a degree of uncertainty. He pledged to attempt another observation when the object becomes visible from Earth in early November, after its passage behind the Sun. His response was measured, scientific, and appropriately cautious, which makes the reaction to his image even more revealing. Within a 24-hour period, numerous websites published articles specifically dedicated to debunking his capture. Headlines declared, "Amateur telescope captures strange 3 Atlas image. Here's why it's not what it seems." The timing felt orchestrated, the tone defensive, as if there was an urgent need to preemptively establish the narrative that nothing unusual had been photographed, and that any perceived anomalies were merely technical glitches before the image could gain significant traction. Subsequently, the enhancement wars commenced. Users across Reddit, Twitter, and various conspiracy-focused forums began downloading the original ESA images and subjecting them to their own processing algorithms. Some employed standard astronomical image stacking techniques. Others utilized AI upscaling tools designed for refining low-resolution photographs. A select few adopted a more radical approach, employing machine learning models trained to reconstruct intricate details from limited data. The outcomes varied dramatically. Some yielded nothing more than slightly sharper iterations of the same indistinct dot. Others revealed what appeared to be distinct geometric patterns, sharp edges, and structures that seemed too regular to be naturally occurring ice and rock. The fundamental issue arises when one engages in aggressive image processing, particularly with AI tools. One is no longer observing what genuinely exists. Rather, one is viewing what an algorithm hypothesizes should be present, based on its training data. If an AI is trained on thousands of images of spacecraft, and then tasked with enhancing a blurred point of light, it might very well generate spacecraft-like features, because that is what it has learned to recognize. This represents a scientific impasse, masked by the illusion of clarity. Nevertheless, the widespread proliferation of these enhanced images produced an unintended consequence. It profoundly obscured the truth, making it nearly impossible to differentiate between legitimate amateur observations and outright fabrications. Within 48 hours of the ESA's image release, dozens of purportedly enhanced versions were circulating online. Some displayed metallic surfaces, others depicted what appeared to be solar panels, antennas, or arrays. A few even included active lights and visible thrusters. The majority were transparently digital art, the product of individuals with excessive time and advanced Photoshop skills. However, intermingled with this deluge of fabricated content were a handful of images that conveyed a subtler, less sensational impression. These images exhibited just enough unusual regularity to provoke contemplation, raising the question of whether something tangible was being deliberately obscured by the torrent of obvious fabrications. Chapter 4: The 4chan Leak That Refuses to Disappear. On the 4th of October, an anonymous user posted on the paranormal board of 4chan, presenting what they claimed to be classified information regarding 3E Atlas. The post was simply titled ESA Data Leak, and commenced with a credential assertion that was specific enough to appear credible, yet sufficiently vague to maintain anonymity. The claim stated, "I am a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of 3I Atlas." Internet leaks are commonplace, and generally easily dismissed as elaborate fiction or deliberate trolling. However, this particular leak possessed a distinct character. The level of technical detail presented was unsettling. The poster avoided sensational claims about extraterrestrial invasions or covert military operations. Instead, they meticulously outlined a series of specific observational anomalies that, if substantiated, would profoundly challenge our prevailing understanding of 3E Atlas's true nature. The first anomaly identified was chemical impossibility. According to the post, spectroscopic analysis indicated that 3E Atlas was emitting approximately 100 kilograms of nickel gas per second, yet exhibiting virtually no ion emissions. Within the established principles of stellar and planetary chemistry, nickel and iron are intrinsically linked. They originate together during supernova explosions, travel in tandem through interstellar space, and are invariably found together in comets and asteroids. The presence of abundant nickel with a near absence of iron is akin to observing smoke without a corresponding fire. It fundamentally contravenes established assumptions regarding the behavior of matter in natural cosmic environments. The second anomaly was termed thermal contradiction. The object was observed to be releasing substantial quantities of gas and dust, a characteristic signature of an active comet heated by the sun. However, infrared observations revealed that it remained remarkably cold, far colder than anticipated given its rate of outgassing and its proximity to solar radiation. The poster likened this phenomenon to witnessing someone profusely sweating in a sub-zero environment. The physics governing the observed phenomena did not align with the empirical data. The third anomaly pertained to trajectory precision. The post referenced Avi Loeb's public statements regarding 3E Atlas arriving with an orbital inclination of merely 4.89 degrees relative to Earth's ecliptic plane. However, the 4chan poster added a crucial detail that Loeb had not emphasized. The trajectory was not merely unusual, but constituted a perfectly straight path originating from the direction of the galactic core. There was no discernible wobble, no deviation, and no indication of gravitational influence from nearby stars during its multi-million or multi-billion year transit through interstellar space, suggesting a directed trajectory. The post then introduced an element that elevated the discussion from intriguing speculation to something more disquieting. The poster posited that the object aligned with the characteristics of what they termed a post-biological entity, neither a natural comet nor a conventional spacecraft, but something falling in between. They described it as possessing a three-phase particle engine with an estimated power output of 75 megawatts, continuously transmitting an active signal and, in their words, probing our solar system. The post concluded with a theoretical framework. The poster suggested that 3 Atlas might represent a macroscopic quantum object, specifically something known as a cue ball. This is an exotic theoretical construct derived from particle physics, a type of non-topological soliton that could, in theory, exist at scales far exceeding those of subatomic particles. If stable, a cue ball could exhibit properties that defy conventional physics. It could possess immense density while appearing diffuse. It could absorb and redistribute energy instantaneously across its entire structure, thereby explaining the observed thermal contradictions. It could even account for the nickel without iron anomaly if the cue ball's internal quantum state preferentially generated specific isotopes. Within 18 hours, the post had been screenshotted and widely disseminated across Reddit, Twitter, and specialized UFO research forums. A thread on the conspiracy subreddit dedicated to discussing it garnered over 2,000 comments before moderators intervened, locking the discussion for violating guidelines against unverified claims. However, the act of locking the thread did not quell the discourse. It merely relocated it to other platforms, fragmenting into dozens of parallel conversations, each diverging in its interpretation of the original post. Some focused on the chemical anomalies, while others zeroed in on the cue ball hypothesis. A subset began drawing connections to earlier assertions that 3 Atlas might have been the source of the 1977 WOW signal. Chapter 5. The 50,000-kilometre question. On the 4th of October, NASA's Perseverance rover, situated in Jezero crater on the Martian surface, captured an image of the night sky above. The photograph, taken by its right navigation camera, revealed an elongated streak of light, approximately 4 times longer than it was wide. At first glance, it resembled a typical long exposure capture of a moving celestial body. Comets and asteroids frequently appear smeared in images when the camera is calibrated to track stars rather than the object itself. This is considered standard observational practice. However, the mathematical calculations did not align with this interpretation. When individuals began to estimate the apparent size of the streak based on Perseverance's known camera specifications and the distance to 3 Atlas at that precise moment, they arrived at a startling figure: 50,000 kilometers in length. This dimension is far beyond that of a comet's nucleus, or even a comet accompanied by a tail. It suggests something entirely different. For comparative purposes, Earth's diameter is less than 13,000 kilometers. If this streak represented the actual physical dimensions of 3 Atlas, the object in question would be nearly 4 times the width of our entire planet. Social media erupted with speculation. Was 3 Atlas in fact a colossal cylindrical vessel? Had it been deliberately concealing its true size and shape behind a diffuse cloud of gas and dust? The timing of this revelation seemed particularly significant. This image emerged just 1 day after the Martian flyby, precisely when all the professional space agencies had fallen inexplicably silent. Some interpreted this as confirmation that something profoundly anomalous had been documented, something that could not be easily dismissed. The speculation reached a level that prompted Representative Anna Paulina Luna, a member of Congress known for her keen interest in unexplained aerial phenomena, to directly contact Avi Loeb for his expert analysis. Consider this for a moment. A sitting member of the United States House of Representatives felt compelled to reach out to a Harvard physicist regarding a photograph originating from Mars. This is highly unconventional protocol. It suggests a level of official concern sufficient to warrant expert interpretation outside the established NASA communication channels. Loeb's response was comprehensive and, on the surface, reassuring. He calculated that the Perseverance navigation camera possesses an angular resolution of 0.33 milliradians per pixel. At the distance of 3 Atlas when the image was captured, approximately 38 million kilometers, This translates to about 12,500 kilometers per pixel. The streak in the image spans roughly 4 pixels, yielding the 50,000 kilometer measurement. However, Loeb argued that this was an artifact of composite imaging. The streak, he contended, did not represent the object's actual size, but rather the path it traced across the Martian sky during an extended integration period, likely comprising about 10 minutes of stacked exposures. His reasoning was logically sound. Mars orbits the Sun at a velocity of 24 kilometers per second. 3 Atlas was travelling at 67 kilometers per second relative to the Sun in an opposing direction, resulting in a relative velocity of over 90 kilometers per second compared to Mars. Over a 10-minute interval, this equates to precisely 54,000 kilometers of travel, perfectly aligning with the observed streak length. The shape was not indicative of the object itself, but rather the object's motion, blurred across time. Case closed, then. The cylindrical craft theory debunked by fundamental physics and meticulous calculation. Except Lowe's analysis contained a single statement that fueled the imaginations of conspiracy theorists like a life raft. He posited, should the images from the navigation camera represent single captures with an exposure duration under 3.28 seconds, then the luminosity and the apparent length of the celestial object suggest it is not Oumuamua. In such a scenario, the source could be considerably nearer to the camera, capable of appearing as an elongated image with a reduced spatial footprint and a slower velocity. Wait, if these are individual frame recordings, then what Perseverance documented was not Oumuamua at all. It was something else entirely, something closer to Mars. That subtle condition opened a pathway that subsequent explanations could never fully close. Because NASA has not confirmed whether the image is a composite or a single capture, they have withheld the associated data. They have not disclosed the exposure time or the quantity of stacked images. The government shutdown provides an analogous justification here as well. Insufficient personnel to process inquiries. No one available to verify fundamental technical specifics regarding the image acquisition. Chapter 6. 48 Years of Silence. On August 15, 1977, Ohio State University's Big Ear radio telescope intercepted a 72-second surge of radio energy, so extraordinary, so precisely composed, that astronomer Jerry Eamon circled it on the printout and inscribed a single word in red ink. Wow. For nearly half a century, that signal has remained one of the most profound enigmas in the quest for extraterrestrial intelligence. It originated from the direction of Sagittarius, near the constellation's most densely populated star fields. It was narrowband, concentrated on one particular frequency, and it has never been detected again. Hundreds of subsequent observations, thousands of hours of listening time directed at the same sector of the sky, yielded nothing but that solitary burst 48 years prior, followed by an unending quiet. Until Avi analysed the data concerning Oumuamua, he calculated the object's position on August 12, 1977, a mere 3 days before the WOW signal was detected. The result placed it approximately 600 astronomical units from Earth, roughly 600 times the distance between our planet and the Sun. More significantly, however, he determined the direction from which Oumuamua was originating at that time: right ascension 19 hours 40 minutes, declination 19 degrees. The WOW signal, conversely, originated from right ascension 19 hours 25 minutes, declination negative 27 degrees. These two directions are separated by approximately 9 degrees. In the immense expanse of space, with random objects appearing from literally any conceivable direction, the statistical likelihood of such an alignment is about 0.6%. While not impossible, it is profoundly suspect. Lowe did not cease his investigation there. He posed the subsequent logical query. If Oumuamua transmitted the WOW signal from a distance of 600 astronomical units, what would the necessary power output of the transmitter have been? The calculations are straightforward. The detected intensity ranged between 54 and 212 Jansky across a 10 kHz bandwidth. At a distance of 600 AU, this corresponds to a transmitter output between half a gigawatt and 2 gigawatts. For perspective, a standard nuclear reactor on Earth generates approximately 1 gigawatt. Therefore, we are discussing energy levels comparable to a nuclear power plant, concentrated into a narrow radio beam. This is not beyond the capabilities of an advanced civilization. In fact, it is quite reasonable if the objective is to transmit a detectable signal across interstellar distances without squandering energy on omnidirectional broadcasting. There is an additional detail that strengthens the connection, making it more difficult to disregard. The WOW signal was observed at a frequency of 1420.4556 MHz, blue shifted by approximately 10 km per second toward Earth, relative to the hydrogen line. This blue shift indicates that the source was moving towards us. Oumuamua is currently approaching the Sun at about 60 km per second. Lowe proposes that if this object possesses maneuvering capabilities, it could have been travelling at a slower velocity in 1977, subsequently accelerating after detecting habitable zone planets within our solar system. This suggests a reconnaissance pulse, a radar scan to search for evidence of technological civilization before committing to a closer approach. Herein lies the profound frustration associated with this entire connection. It would be remarkably simple to verify. Direct a radio telescope towards Oumuamua, listen at the hydrogen line frequency. If it is transmitting, we would know within hours. If it remains silent, the connection to the WOW signal is likely coincidental. A straightforward test, yielding a definitive answer. Nevertheless, as Lowe observed in his most recent blog post, not a single radio telescope has reported any data concerning Oumuamua. The Very Large Array has not made any observations. The Arecibo telescope has been destroyed. The Green Bank telescope has not published any findings. Even SETI, the organisation explicitly dedicated to discovering extraterrestrial signals, has not publicly announced any monitoring efforts. The silence emanating from the radio astronomy community is deafening. Chapter 7. The Path That Should Not Exist. Imagine tossing a dart at a globe from across a room while blindfolded. Now, envision that dart not only striking the globe but landing within a few degrees of the equator. That approximates the statistical improbability we're confronting when examining Oumuamua's entry into our solar system. Objects originating from interstellar space can arrive from literally any direction. They should exhibit a random distribution across the celestial sphere, entering at all possible angles. Yet, Oumuamua arrived with an orbital inclination of merely 4.89 degrees relative to Earth's ecliptic plane, less than 5 degrees. This places it within the least than 1% of potential arrival angles. A.V. Lowe has consistently emphasized this point in every interview, every blog post, and every public statement since July. The trajectory is anomalous, not merely unusual, but statistically profoundly improbable for a random interstellar object. To comprehend why, one must consider the mechanics of object movement within the galaxy. Stars in the Milky Way's disk orbit the galactic center with a certain average velocity. However, they also possess random motions, both vertically and laterally, akin to bees swarming around a hive. This inherent randomness dictates that objects ejected from other star systems should reach our solar system from all directions with approximately equal probability. There is no preferential direction, no cosmic thoroughfare that funnels interstellar visitors into our ecliptic plane. And before anyone suggests that perhaps objects from the galactic disk naturally arrive at shallow angles, Lowe has addressed that as well. The galactic disk itself is tilted approximately 60 degrees relative to our solar system's ecliptic plane. 60 degrees. That is more than 10 times greater than the inclination of Oumuamua. If this object originated from a typical star system within the galactic disk and was ejected randomly, we would anticipate its arrival at a steep angle, not a shallow one. The alignment is inverted from what galactic geometry would predict. Compare Oumuamua to the only other interstellar objects we have detected. Oumuamua, discovered in 2017, arrived with an inclination of 123 degrees, wildly tilted, entering from above the solar system's plane. Borisov, spotted in 2019, exhibited an inclination of 44 degrees, still steep, still consistent with a random arrival from interstellar space. Both of those objects behave precisely as expected for natural interstellar visitors. Oumuamua stands as the outlier, the anomaly, the one that deviates from the established pattern. Low calculated the probability of this alignment, assuming random directions, to be less than 1%. Some colleagues voiced dissent, suggesting his statistical analysis might be overly conservative. Perhaps the actual probability is closer to 5 or 10% when accounting for various selection effects and observational biases. Very well. Even at 10%, one is still examining a phenomenon that should occur only once in every 10 interstellar objects we detect. And thus far, we have detected only 3. The odds of the third object being the rare exception rather than the rule do not favour mere coincidence. Now consider this in conjunction with all other factors. The alignment with the WOW signal also carries a probability of less than 1%. The chemical anomalies, specifically nickel without iron, the thermal inconsistencies, the absence of high-resolution images from multiple space agencies, the government shutdown occurring precisely when NASA's capabilities are most crucial. Any single one of these occurrences could be dismissed as coincidence, a measurement error, or bureaucratic incompetence. However, when one begins to accumulate anomalies, when one starts multiplying small probabilities, the combined improbability becomes increasingly difficult to disregard. There exists a statistical principle known as the prosecutor's fallacy. It is the error of treating multiple independent low-probability events as interconnected, when they are, in fact, merely random coincidences that happen to cluster together. If you flip a coin enough times, you will eventually achieve 10 consecutive heads. This does not imply the coin is rigged. It simply means you have flipped it a sufficient number of times for unlikely sequences to manifest. Skeptics will contend that this is precisely what we are observing with Oumuamua, a natural comet possessing several unusual but ultimately explainable characteristics that coincidentally converged in the same object. Unlikely, certainly, but not impossible. The counterargument is equally valid. If an entity walks like a duck, quacks like a duck, swims like a duck, and possesses duck DNA, at a certain point, one must entertain the possibility that it is in fact a duck. Or, in this instance, if an object arrives on a statistically improbable trajectory, displays chemical signatures inconsistent with natural processes, correlates with a 48-year-old unexplained radio signal, and prompts multiple governments to withhold their most advanced imaging data, perhaps it is prudent to seriously consider that we're not observing a random fragment of ice and rock from another star system. Chapter 8. When Questions Become Dangerous. A peculiar phenomenon began to emerge around October 5th. Users across various platforms started reporting that their posts concerning Oumuamua were disappearing, not merely being flagged or labelled as misinformation, but actually vanishing. A Reddit user documented creating a detailed thread analysing the chemical anomalies derived from the purported ESA leak. The thread gained considerable traction, accumulating hundreds of upvotes and dozens of comments within 2 hours. Subsequently it was gone, not removed with a moderator's explanation, but simply deleted from existence. When the user attempted to repost it, the submission failed to go through. They were shadow banned without any notification or justification. On Twitter, now X, several accounts observed similar patterns. Astronomy Vibes, the account that achieved viral status for criticizing the ESA photographs, reported a significant decline in engagement subsequent to October 7th. Posts that would typically reach tens of thousands of individuals were abruptly plateauing at a few hundred views. There were no official restrictions, no warning messages, simply algorithmic suppression, subtle enough to be deniable, yet potent enough to be effective. Other content creators within the space astronomy community noted the same trend. Videos discussing Oumuamua that normally performed well were receiving only a fraction of their typical reach. YouTube presented a distinct challenge. Content creators who uploaded analytical videos speculating about Oumuamua began receiving demonetization notices. The stated reasons varied. Some were flagged for discussing sensitive topics without adequate context. Others were categorized as potentially misleading content concerning scientific matters. A few were subjected to the vague yet ominous designation of content that may not be suitable for all advertisers. The pattern was undeniable. One could create a video asserting with certainty that Oumuamua is merely a comet, and that mainstream science has definitively explained it. That was acceptable, monetized, and promoted. However, suggesting that there might be anomalies warranting investigation would suddenly render one's video unfavorable to advertisers. Facebook's approach was the most overt. The platform's fact-checking system, managed by third-party verification organizations, commenced aggressively labeling content related to Oumuamua. Posts sharing the 4chan leak were subjected to missing context warnings. Claims regarding trajectory anomalies were labeled as partially false, even when the posts were merely quoting Avilo's published calculations verbatim. The accompanying fact-check articles offered a measure of reassurance. Space agencies confirm no threat from interstellar comet. Experts say unusual features likely natural processes. The underlying message was clear. Do not worry, refrain from speculation, trust the authorities, move along. The timing felt orchestrated. All of this intensified within 48 hours of the ESA photo release, precisely when public frustration was at its peak regarding the lack of high-quality images. This pattern tends to either vindicate conspiracy theorists or cause skeptics to dismiss it as overreaching paranoia. The reality is, social media platforms suppress content routinely. Algorithms undergo changes, engagement fluctuates, fact-checkers flag misinformation. These are standard platform operations not indicative of coordinated censorship, unless a discernible pattern emerges. Unless it is all occurring simultaneously, targeting a single specific topic, precisely when public interest is highest, and official explanations are most conspicuously absent. Some creators began employing coded language to circumvent suppression. Instead of referring to Oumuamua, they would use terms like the visitor or the object. Instead of alien or extraterrestrial, they would opt for non-terrestrial or anomalous. It was akin to observing the development of a new lexicon to discuss subjects the platforms preferred not be openly debated. The Streisand effect in real time. The more the content was suppressed, the greater the assumption that there was something worth concealing. The more aggressively fact-checkers pushed back, the less trust the public placed in the official narrative. Every effort to control the discourse only amplified the suspicion that such control was necessary. Chapter 9. The Moment We Cannot Watch. Mark October 29th and 30th on your calendars. In less than 72 hours from now, Oumuamua will reach perihelion, its closest approach to the Sun. It will pass at a distance of approximately 202 million kilometers, just inside the orbit of Mars. For a natural comet, this represents the critical juncture. The intense solar radiation at this proximity is expected to trigger dramatic outgassing, possibly even fragmentation. We have witnessed this phenomenon before. Comets approach the Sun, the heat becomes overwhelming, and they break apart into smaller pieces. A spectacular event when it occurs. And if Oumuamua is indeed an ordinary chunk of ice and rock from another star system, this is precisely what should transpire. However, here lies the predicament. We will be unable to observe it. Oumuamua will be positioned on the opposite side of the Sun from Earth during its perihelion passage. Every ground-based telescope on our planet will be rendered useless. The object will be obscured by the solar glare, completely hidden from observation during what should be its most active and revealing phase. Some are labelling this as unfortunate timing, others perceive it as suspiciously convenient. If one intended to undertake an action without being observed, a more opportune window could not be selected. Avi Lowe has been explicit regarding the subsequent events. In his blog post dated October 3rd, published on the day of the Mars flyby, he outlined two potential scenarios. If Oumuamua is a natural comet, it may soon erupt in a flare of outgassing or fragment into icy pieces. The sunlight will impart gigawatts of power onto its surface. This energy must dissipate somewhere. For ice and rock, this manifests as vaporization, sublimation, and potentially structural failure. However, Lowe then introduced an alternative possibility. Alternatively, if it is technological, it may maneuver to benefit from the Sun's gravitational assist or release probes that could intercept Earth or other planets, owing to its retrograde orbit, which is opposite in direction to the motion of the planets around the Sun. Read that again. Release probes that could intercept Earth. He is no longer discussing passive observation. He's alluding to active deployment. The retrograde orbit is a crucial element. Oumuamua is travelling in opposition to the direction in which planets orbit the Sun. This implies that any probes it might release would not need to contend with planetary motion to reach us. They could simply enter an intercept trajectory, allowing orbital mechanics to facilitate their journey. Emerging from behind the Sun, concealed from our view, launching something towards Earth that would go undetected until it was in close proximity, would be remarkably straightforward. Lowe elaborated further, writing, "When you look at the Sun in the coming weeks, keep in mind that Oumuamua is passing behind it. If Oumuamua maneuvers towards Earth when it reappears on the other side of the Sun, the financial markets may crash. Financial markets may crash." This is not metaphorical language. It is not hyperbole. He is suggesting that if this object demonstrates technological capability, if it alters its course towards Earth following perihelion, the economic and social repercussions would be immediate and severe. Financial markets are sensitive to uncertainty. The uncertainty presented by a potentially hostile interstellar object actively altering its trajectory toward our planet would represent existential-level uncertainty. The confluence of events amplifies the tension. The government shutdown means NASA is non-operational during this critical observation window. The most compelling images from the Mars flyby remain unreleased. Amateur astronomers are unable to observe the object for the next month, due to its position behind the Sun. Radio telescopes have not been utilised for detection. We are effectively flying blind into the most pivotal moment of this entire encounter, and whether through incompetence or deliberate design, we have created a situation where we will not ascertain Oumuamua's actions at perihelion until they have already occurred. There is one entity diligently observing. The Galileo project, led by Lowe himself, operates 3 observatories, one in Massachusetts, one in Pennsylvania, and one in Nevada. These facilities are equipped with high-resolution cameras, infrared sensors, and radio receivers specifically engineered to detect anomalous aerial phenomena. Throughout late October and early November, all 3 observatories will be functioning at maximum capacity, monitoring the skies for any unusual activity. If Oumuamua releases probes, or if there is an increase in UAP activity correlated with its perihelion passage, the Galileo instruments may capture it. May being the operative word. 3 observatories covering a limited portion of Earth's sky. If something arrives and avoids these specific observation zones, we will entirely miss it. Chapter 10. What comes after? Early November. That is when Oumuamua will re-emerge from behind the Sun and once again become visible from Earth. Ground-based telescopes will be capable of tracking it once more. We will be able to ascertain whether it survived perihelion intact or fragmented under solar stress. We will measure its trajectory to determine if any course corrections were made, and we will finally know whether the past 4 months of speculation, conspiracy theories, and unanswered questions were warranted or merely collective hysteria surrounding a completely natural interstellar visitor. If Oumuamua reappears on the same trajectory it entered with, if it exhibits clear indications of fragmentation or increased outgassing consistent with solar heating, if it behaves precisely as Borisov did during its solar approach in 2019, then the mystery is essentially resolved. A natural comet, with unusual chemistry perhaps, a statistically improbable trajectory, granted, but ultimately just an icy remnant from another star system traversing ours. The connection to the WOW signal would become a coincidence. The 4chan leak would be reinterpreted as creative fiction. The missing NASA images would be attributed to bureaucratic delays during a government shutdown. Everything would then re-enter the comfortable framework where interstellar objects are intriguing but not alarming. However, if this is not the case, if Oumuamua reappears with an altered trajectory, if it demonstrates even subtle course corrections that cannot be explained by outgassing thrust, if radio telescopes finally direct their attention towards it and detect structured transmissions, if the NASA images eventually surface and reveal geometric structures that should not exist on a natural object, then we'll find ourselves in entirely uncharted territory. Not solely from a scientific perspective, but socially, politically, and economically as well. Every fundamental assumption about our place in the cosmos will be challenged. Every nation's reaction to the prospect of encountering extraterrestrial life is being scrutinized in real time. Aviv has devised a system he labels the Loeb scale. This is a classification framework to evaluate the likelihood of an object originating from artificial sources and the degree of peril it might present. A rating of 1 signifies a virtually certain natural phenomenon, exhibiting intriguing but understandable discrepancies. A rating of 10 denotes a definite artificial object, displaying evident hostile intentions and the capacity to reach our planet. He publicly declared his refusal to assign the object referred to as 3I Atlas, a rank lower than a 2. Even in the most optimistic outlook, the anomalies observed are too persistent, too abundant, and too interconnected. A rating of 2 implies a probable natural origin, yet with sufficient unexplained characteristics to necessitate thorough examination. It signifies that we cannot definitively dismiss an artificial source without acquiring additional information. This is our current predicament, teetering between classifying it as a naturally occurring celestial body and a potential manufactured artifact. We are anticipating the month of November, awaiting high-resolution imagery that may never materialize. We are awaiting radio observations that have yet to be conducted. We are awaiting 3I Atlas to either continue its hyperbolic trajectory away from our solar system, vanishing forever, or to perform an action that compels us to acknowledge the reality that we're not alone and we are unprepared. The European Space Agency has announced that its Jupiter Icy Moons Explorer spacecraft, JUICE, will conduct observations of 3I Atlas between November 2nd and 25th, utilizing a variety of sophisticated instruments. This observation period will commence shortly after perihelion, when the object is expected to be at its peak activity. The gathered data will not be accessible until February of 2026 due to communication delays and the time required for data processing. This means a waiting period of 7 months for images captured in November. 7 months of uncertainty regarding whether the heightened activity observed by JUICE is typical cometary outgassing or something entirely different. 7 months of speculation as to whether the indistinct celestial body showcased by the ESA in October was the best they could provide, or if they are deliberately managing a disclosure they are uncertain how to convey. Regardless of what 3I Atlas is, and irrespective of its actions in the coming weeks, the discourse surrounding it has already illuminated a critical aspect of our societal state. We lack faith in our institutions to impart truthful information on matters of such consequence. We are skeptical of official assurances. We perceive patterns in the timing of system shutdowns and data latency, which may or may not be actual occurrences. We are predisposed to conspiratorial thinking because we have learned, sometimes through harsh experience, that conspiracies are not always mere speculation. Occasionally they represent early intelligence on events that later become verified facts. Chapter 1. The Unseen Visitor. On the first day of October, in the year 2025, an entity approximately the size of a giraffe traversed the space between Earth and our orbiting satellites. It approached our planet closer than the International Space Station's orbital path. Its arrival was entirely unanticipated. By the time astronomers detected it, asteroid 2025 TF had already completed its pass, receding into the obscurity of space like a phantom that neglected to announce its presence. Reflect on this for a moment. We inhabit an era where we possess the capability to capture images of distant galaxies in their nascent stages billions of years ago. Yet, a celestial fragment of rock close enough to nearly graze our atmosphere went entirely undetected until it was already in our rearview mirror. If you find this as disconcerting and captivating as I do, please consider liking and subscribing to remain informed about these near misses in space and the enigmas unfolding above us. Please share in the comments your listening location, the current time there, and whether you believe we should experience more apprehension or more wonder regarding the extent of what remains unseen in our night sky. And if you wish to contribute to the growth of our community, kindly share these videos on X, Facebook, Reddit, or via your messenger. We appreciate your unwavering support. The asteroid's dimensions were estimated to be between 1 and 3 meters in width. It was sufficiently small that had it entered our atmosphere, it would have disintegrated in a spectacular fiery display, posing no threat to cities or civilizations. However, it is precisely this scenario that causes astronomers sleepless nights. If we are incapable of reliably detecting an object at such proximity, an object travelling at speeds that would traverse the distance between New York and Los Angeles in under 60 seconds, what other phenomena might we be overlooking? The European Space Agency and NASA diligently monitor thousands of near-Earth objects, meticulously cataloguing those that present the most significant risk of collision. To be categorized as potentially hazardous, an asteroid must possess a diameter of at least 140 meters and follow an orbit that brings it within 7.5 million kilometers of Earth, approximately 20 times the distance separating us from the Moon. Asteroid 2025 TF falls considerably short of this size criterion, which partially accounts for its elusiveness to detection. Our telescopes and surveillance systems are programmed to prioritize the identification of larger celestial bodies, those capable of ending civilizations, the objects that could trigger another extinction-level event if they impacted at an unfavorable angle. Yet this diminutive visitor serves as a stark reminder that the cosmos is not an empty void. It is in constant flux with debris, ancient fragments originating from the solar system's formation, shards of disintegrated worlds that never achieved planetary status, remnants of collisions that occurred during Earth's infancy. The majority of this material remains in distant locations, confined within stable orbits in the asteroid belt situated between Mars and Jupiter, or drifting in the remote Kuiper belt beyond Neptune. However, gravitational interactions, the subtle gravitational influence of Jupiter's immense mass, or a gentle nudge from a passing comet can alter these orbits, propelling rocky bodies onto new trajectories that occasionally intersect with our own. What renders 2025 TF particularly noteworthy is not merely its close proximity, but its passage during a month when the celestial sphere appears unusually active with visitors. Chapter 2: The Luminous Drifter. While one celestial traveller passed by us without announcement, another is making a far more ostentatious arrival. Comet C 2025 A6, more commonly known as Lemon, named after the observatory that discovered it, is increasing in brightness in our October skies. Astrophotographers globally have been capturing increasingly stunning images as this mass of ancient ice and dust journeys towards a close encounter with Earth. Unlike the stealthy asteroid that caught us by surprise, Lemon has been diligently tracked since its initial discovery. Currently it resides at the very edge of naked eye visibility. Over the ensuing weeks, provided conditions are favourable and the skies are sufficiently dark, you might have the opportunity to step outside and observe it with your own eyes. It will appear as a faint, hazy patch of light, trailed by a spectral tail extending away from the Sun. Comets are fundamentally distinct from asteroids. Whereas asteroids are solid, rocky, or metallic fragments that originated in the warmer inner regions of the solar system, comets are icy bodies that formed in the frigid outer reaches. They are sometimes referred to as dirty snowballs, though this description is an oversimplification. The nucleus of a comet comprises frozen water, carbon dioxide, methane, and ammonia, intermingled with dust and organic compounds, the fundamental chemical constituents of life. As a comet approaches the Sun, solar radiation warms its surface, causing the ice to sublimate directly, transitioning from a solid to a gaseous state without liquefying. This process generates the coma, a transient atmosphere of gas and dust that can extend for hundreds of thousands of kilometers. The solar wind and radiation pressure then propel this material away from the nucleus, forming the characteristic tail that consistently points away from the Sun, irrespective of the comet's direction of travel. Lemon is not the sole comet gracing our skies this month. Another visitor, C225 R2, identified as Swan, will pass Earth later in October at a distance of 0.26 astronomical units. This is sufficiently close to offer a spectacle for those equipped with binoculars or small telescopes. Both comets currently shine at approximately magnitude 6, right at the limit of human visual perception under optimal conditions. However, comets are notoriously unpredictable celestial bodies. They can experience sudden flares in brightness if their rotation exposes fresh ice to solar radiation, or if an outburst ejects a plume of material into space. They are also prone to fragmentation, breaking apart under the strain of solar heating or tidal forces, resulting in multiple nuclei, each subsequently developing its own coma and tail. The allure of observing comets extends beyond their visual beauty. It lies in their connection to primordial time. The ice within these celestial objects formed billions of years ago in the outer solar system, preserved in a cosmic deep freeze, far removed from the Sun's warmth. When we witness a comet, we are beholding material that existed prior to Earth possessing oceans, before the Moon had fully formed, and before life emerged, perhaps from a warm tidal pool or a deep-sea vent, initiating the process of self-replicating chemistry. Some scientific minds posit that comets delivered substantial quantities of water to early Earth, raining down in a cosmic bombardment that contributed to filling our oceans. Others suggest that the organic molecules discovered within comets, including amino acids, the fundamental components of proteins, may have seeded our planet with the raw materials necessary for life's inception. This linkage between ancient comets and the genesis of life brings us to another groundbreaking discovery that is prompting scientists to re-evaluate the prevalence of life's essential ingredients throughout the cosmos. Chapter 3. A Cradle for Moons. 625 light-years distant from Earth, a remarkable phenomenon is unfolding around a young planet. The James Webb Space Telescope has obtained the inaugural direct measurements of a moon-forming disk, a rotating ring of gas and dust encircling an exoplanet designated CTB. Within this disk, Webb has detected chemical signatures that hold the potential to give rise to moons. These include hydrogen cyanide, acetylene, benzene, propene, ethane, and carbon dioxide, all carbon-bearing molecules swirling within a structure that bears a striking resemblance to planetary scientists studying the historical trajectory of our own solar system. The significance of this finding lies in the fact that for decades we have theorized about the process of moon formation, but we have never actually witnessed it in action. Jupiter's 4 largest moons, the Galilean satellites first observed by Galileo in the year 1610, orbit their host planet in a flat plane, suggesting they coalesced from a disk of material that once surrounded Jupiter billions of years ago, much like the planets themselves formed from a disk surrounding the young Sun. The 2 outermost of these moons, Ganymede and Callisto, are composed of 50% water ice, although they likely possess rocky cores of carbon or silicon beneath their frozen exteriors. Based on their orbital characteristics and compositions, scientists have long hypothesized that a circumplanetary disk once existed around Jupiter. Within that disk, the foundational materials for moon formation gathered and aggregated. Now with CTB, we're observing a comparable process unfolding in real time. Although it is crucial to remember that real time in an astronomical context can be somewhat misleading. The light we are detecting from this system originated 625 years ago, a period when Earth was immersed in the Renaissance, and the concept of planets beyond our own solar system had not yet been conceived. Nevertheless, from our vantage point, we are witnessing moon formation as it occurs, and the details are truly captivating. The planet itself orbits a star that is merely 2 million years old, a star that is still actively accreting material from its own circumstellar disk. This signifies that we are observing a system in its nascent stages, a planetary nursery where multiple cycles of structural formation are occurring concurrently. What most astonished the researchers was the stark chemical disparity between the planet's moon-forming disk and the star's planet-forming disk. The circumplanetary disk surrounding CTB is abundant in carbon-bearing molecules, but exhibits no indication of water. Conversely, the circumstellar disk around the star contains water, but lacks the carbon-based chemistry observed in the planet's disk. This chemical separation has transpired in a mere 2 million years, suggesting that disk chemistry undergoes rapid evolution and follows divergent paths contingent upon localized environmental conditions. Factors such as temperature, radiation levels, and the presence of magnetic fields all influence which molecules can persist and which are degraded. The implications extend beyond comprehending the mechanics of moon formation. By mapping the chemical composition of these disks in nascent systems, we can begin to forecast which exoplanets are likely to harbour moons, and, subsequently, which of those moons might possess conditions conducive to supporting life. Within our own solar system, certain locations offer the most promising prospects for the search for life, not among planets, but among moons. Europa, orbiting Jupiter, is believed to possess a liquid water ocean beneath its icy crust, maintained at a habitable temperature by the tidal forces exerted by Jupiter's gravitational pull. Enceladus, a small moon of Saturn, expels geysers of liquid water into space from a subterranean ocean. Within these geysers, scientists have detected organic molecules. If moons orbiting other stars form with analogous characteristics, then the number of potentially life-sustaining worlds in our galaxy would increase exponentially. Our search would need to encompass not only planets situated within the habitable zone of their stars, but also moons orbiting giant planets anywhere within a planetary system. This broadened perspective on the potential origins of life converges with the technological advancements we are currently developing here on Earth. These are technologies that may, in the future, facilitate our exploration of these distant worlds, or at least enhance our comprehension of them. Chapter 4: The Quantum Leap. The United Nations has officially designated the year 2025 as the International Year of Quantum Science and Technology, marking precisely 100 years since the foundational development of quantum mechanics. This timing is particularly fitting, as 2025 is poised to be the year when quantum computing transitions from a subject of academic curiosity to a realm approaching practical application. In November of 2024, Microsoft and Atom Computing announced their successful creation and entanglement of 24 logical qubits. This represents a significant technical achievement, marking a substantial stride towards the construction of quantum computers capable of resolving genuinely useful problems. To grasp the importance of this development, we must first elucidate the fundamental differences between quantum computers and the device you're presently using to access this information. Conventional computers, whether they are smartphones or supercomputers, process data using bits, which are fundamental units representing either a 0 or a 1, an off or on state, a false or true condition. Every operation performed by your computer, from streaming video content to executing complex simulations, ultimately relies on the manipulation of an immense quantity of these binary digits at extraordinary speeds. Quantum computers operate on entirely distinct principles. Instead of bits, they utilize qubits, or quantum bits, which possess the remarkable ability to exist in a state of superposition, simultaneously embodying both 0 and 1 until they are subjected to measurement. This is not merely a conceptual abstraction or a clever technique. At the quantum level, particles genuinely inhabit multiple states concurrently, a direct consequence of the wave-like nature of matter as described by quantum mechanics. When multiple qubits are in a state of superposition, they can represent an exponentially greater volume of information compared to an equivalent number of classical bits. For instance, 2 classical bits can represent 4 distinct values, 0, 0, 1, 0, 0, 1, or 1, 1, but only one of these at any given moment. Conversely, 2 qubits in superposition can simultaneously represent all 4 of these values. Similarly, 3 qubits can represent 8 distinct values at once. This scaling effect continues exponentially, meaning that a quantum computer equipped with just a few hundred qubits could theoretically perform calculations that would require classical supercomputers a duration exceeding the age of the universe. However, there has always been a significant obstacle. Qubits are extraordinarily fragile. They lose their quantum properties, a process known as decoherence, when they interact with their surrounding environment. Fluctuations in temperature, stray electromagnetic fields, or even the passage of cosmic rays through a laboratory can induce errors. This necessitates the cooling of quantum computers to temperatures approaching absolute zero and their rigorous shielding from external interference. Even with these precautions, errors accumulate so rapidly that computations become unreliable before their completion. The pivotal breakthrough that renders the years 2024 and 2025 so momentous is the progress achieved in quantum error correction. This refers to the capacity to identify and rectify these errors without compromising the quantum state that is being preserved. The creation of 24 entangled logical qubits signifies the development of qubits with integrated error correction mechanisms, rendering them considerably more stable and dependable than the physical qubits that constitute the fundamental hardware. Entanglement is another quantum phenomenon that Albert Einstein famously described as spooky action at a distance. When qubits become entangled, the act of measuring the state of one instantaneously influences the state of the others, irrespective of the spatial separation between them. This capability enables quantum computers to execute certain types of computations, such as database searches or the factoring of large numbers, with far greater efficiency than classical computers could ever achieve. The global competition to develop practical quantum computers is currently intense and highly dynamic. In early 2025, Japan announced a substantial investment of $7.4 billion in quantum technology. Spain committed $900 million. These investments collectively bring the total public funding allocated for quantum research to well over $10 billion, underscoring government's recognition of quantum computing not merely as a scientific curiosity, but as a strategic technology with the potential to revolutionize diverse fields, ranging from drug discovery to cryptography and artificial intelligence. The private sector is demonstrating an equally significant commitment. Prominent companies such as Google, IBM, and Amazon are continuously pushing the boundaries of what is technologically feasible. Google has asserted that its quantum processors can solve specific problems at an exponentially faster rate than conventional supercomputers. IBM has outlined a strategic roadmap aimed at constructing a system with 200 logical qubits by the year 2028. Concurrently, numerous startups are exploring alternative approaches, employing photons instead of superconducting circuits or utilizing trapped ions rather than solid-state devices. Each of these methodologies presents its own distinct advantages and challenges. However, beyond the impressive engineering accomplishments, there is a profoundly philosophical dimension to quantum computing that captivates the human imagination. These machines operate based on principles that fundamentally contradict our everyday intuition regarding the nature of reality. Yet, these very principles appear to be integral to the fabric of the universe itself. The same quantum mechanics that enables the existence of qubits also governs the behavior of atoms, the structural arrangement of molecules, and the emission of light from stars. In essence, quantum computers are empowering us to harness the intrinsic language of the universe to address problems that would otherwise remain intractable. One such pressing problem involves comprehending and controlling the process of nuclear fusion, a subject that brings us to another set of significant advancements that occurred within the same temporal framework. Chapter 5, Capturing the Stars, on February 12, 2025. Scientists at the West Tokamak reactor in France established a new global benchmark. They successfully sustained superheated plasma for a duration of 22 minutes and 17 seconds, surpassing the prior record by over 4 minutes. The plasma attained a temperature of 50 million degrees Celsius, approximately 3 times the temperature found at the core of the Sun. To individuals unfamiliar with fusion research, this achievement might not immediately appear as progress. After all, the Sun has been sustaining fusion reactions for 4.5 billion years without any external intervention. However, the creation and containment of a stellar-like process here on Earth represent one of the most formidable challenges in the entirety of scientific and engineering endeavour. Fusion operates by compelling atomic nuclei to collide with such immense force that they overcome their inherent electromagnetic repulsion and merge, thereby releasing substantial energy. In the Sun, this process occurs due to the colossal mass of the star, which generates overwhelming gravitational pressure at its core, coupled with temperatures reaching 15 million degrees. On Earth, we lack this gravitational advantage. Consequently, we require even higher temperatures to achieve fusion. Furthermore, we must devise a method to contain plasma at such extreme temperatures without allowing it to come into contact with any physical surface, as no material can withstand such heat without instantly vaporizing. The ingenious solution lies in magnetic confinement. Tokamaks employ powerful magnetic fields to construct a cage of force that ensnares the plasma within a toroidal or donut-shaped region, suspending it in a vacuum, thereby preventing any contact with the vessel walls. The West reactor's accomplishment of sustaining plasma for 22 minutes is particularly significant because future fusion power plants will necessitate continuous operation rather than intermittent bursts. It is not economically viable to generate electricity if a reactor must be repeatedly shut down and restarted every few minutes. The current record signifies that the intricate engineering obstacles inherent in steady-state operation, encompassing heat flow management and the stabilization of plasma against disruptive instabilities affecting magnetic confinement, are gradually being overcome. The preceding benchmark, set at a little over 17 minutes, was held by China's East Tokamak, achieved in January of 2025, indicating that 2 significant advancements in plasma duration have occurred within mere weeks of each other. These are not the sole advancements in fusion technology presently unfolding. ETA Technologies, a private fusion enterprise, declared in April of 2025 a substantial simplification in their method of plasma generation and stabilization. Their methodology employs a structure known as a field-reversed configuration, or FRC, a magnetic arrangement that is more compact than a conventional tokamak. Previously, the creation of an FRC necessitated elaborate formation sections at each extremity of the device, where plasma was initially generated, subsequently accelerated, and then collided at high velocities within the central region. ETA has devised a means to generate and stabilize an FRC plasma directly at the core of their apparatus solely through neutral beam injection. thereby eliminating the need for complex upstream formation hardware. This innovation leads to reduced costs, enhanced efficiency, and propels them closer to demonstrating a net energy gain before the conclusion of the current decade. Concurrently, the private fusion sector as a whole is experiencing rapid expansion. Commonwealth Fusion Systems is in the process of constructing a pilot facility named Spark, situated near Boston, with a projected operational commencement in 2027. Helion has successfully completed initial assessments on their most recent apparatus, engineered to achieve break-even utilizing a distinct magnetic confinement strategy. General Fusion, headquartered in Canada, is developing a demonstration system that employs an entirely different methodology, involving the mechanical compression of plasma rather than exclusive reliance on magnetic fields. The variety of approaches employed reflects both the inherent difficulty of the challenge and the acknowledgement that multiple pathways may lead to successful fusion energy generation. In December of 2022, scientists at the National Ignition Facility attained fusion ignition for the initial instance, a reaction that yielded more energy than was expended by the lasers to initiate it. This was a scientific milestone, a definitive confirmation that controlled fusion is physically achievable. However, transforming this proof of concept into a functional power plant necessitates overcoming numerous engineering hurdles. The fusion fuel, typically a blend of deuterium and tritium, both isotopes of hydrogen, must be continuously replenished. The neutrons generated by fusion reactions carry immense energy and render the reactor's internal walls radioactive. Consequently, materials must be capable of withstanding years of neutron bombardment without degradation. The heat generated must be efficiently captured and converted into electrical energy. All of these processes must occur at a cost that is competitive with other energy sources. What makes fusion so exceptionally appealing, notwithstanding these challenges, is the promise of nearly inexhaustible clean energy. Deuterium can be extracted from seawater, where it naturally occurs at a ratio of 1 atom for every 6,500 hydrogen atoms. At this concentration, the world's oceans contain sufficient deuterium to power human civilization for millennia. Tritium is rarer and must be bred from lithium, but lithium is readily available. Fusion produces no long-lived radioactive waste. Unlike fission reactors, it generates no carbon emissions, and a fusion reactor cannot experience a meltdown or explosion, as the plasma is so diffuse that any disruption simply causes the reaction to cease. The fundamental question is no longer whether fusion will be viable, but rather when it will become practical and economically feasible. Optimists point to the swift advancements in both governmental and private sector initiatives, suggesting that the first commercial fusion electricity might be integrated into the grid by the early 2030s. Skeptics, however, note that fusion has consistently been predicted to be 20 years away for the past 60 years and caution that unforeseen complications invariably arise. Nevertheless, the momentum observed in 2025 feels distinct. It is propelled by a confluence of technological breakthroughs, substantial investment, and the pressing imperative for clean energy solutions to address climate change. For the first time, it appears plausible that a child born today might grow up in an era where fusion power is as commonplace as solar panels or wind turbines. Furthermore, perhaps that child's generation will utilize fusion-powered spacecraft for interplanetary exploration, charting the paths of ancient comets and asteroids, and investigating celestial bodies we have only glimpsed from afar. One such moon, Mars, continues to offer intriguing clues suggesting it may have once harboured life. Chapter 6: Leopard Spots on Mars. In July of 2024, NASA's Perseverance rover extracted a core sample from a rock formation, colloquially referred to as Chava Falls, situated within Mars' Jezero crater. This geological specimen displayed characteristics that mission scientists deemed the most enigmatic, intricate, and potentially significant they had encountered. Following a year of stringent peer review, the findings were disseminated in the journal Nature in September of 2025, and they represent the most compelling evidence to date that Mars may have once been a habitat for microbial life. The operative word here is may, because one of the most arduous lessons in astrobiology is that initial appearances can be profoundly misleading. Chava Falls is located within an ancient riverbed, in a region Perseverance has been investigating known as Bright Angel. Billions of years ago, water once flowed through this area, carving channels as it converged upon Jezero Crater, which at that time was a vast lake. The rock itself is sedimentary, composed of clay and silt, precisely the kind of material that, on Earth, serves to preserve fossils and chemical remnants of ancient life. Perseverance's instrumentation detected organic carbon, sulfur, oxidized iron, and phosphorus. This combination frequently signifies biological activity on Earth. However, what truly captivated the scientists were minute formations they have termed leopard spots. These are tiny specks, enriched with iron phosphate and iron sulfide, dispersed throughout the rock in a manner reminiscent of markings on an animal's coat. On Earth, when microorganisms metabolize organic matter, they frequently generate iron phosphate and iron sulfide as metabolic byproducts. The spatial distribution of these compounds within Chava Falls closely resembles that observed in terrestrial rocks containing fossilized microbial communities. Yet, herein lies the conundrum. Chemical processes alone can also generate analogous patterns devoid of biological involvement. Hydrothermal activities and volcanic eruptions, for instance, can produce iron-rich mineral deposits. The central challenge lies in differentiating between biological and non-biological origins based solely on chemical composition and texture, particularly when conducting such analyses remotely with instruments aboard a rover millions of kilometers away. This inherent ambiguity is precisely why scientists employ the term potential biosignature. Rather than definitively claiming the discovery of life, a potential biosignature denotes a substance or structure that could possess a biological origin, but requires further data or extended investigation before any definitive conclusions can be drawn. This represents a deliberately cautious and conservative approach, as the assertion of having discovered evidence of extraterrestrial life, even extinct microbial life, is an extraordinary claim demanding extraordinary corroboration. The scientific community has learned this lesson through past controversies, such as the widely publicized announcement in 1996 that a Martian meteorite discovered in Antarctica contained purported fossils of bacteria, a claim that subsequent research could neither definitively confirm nor refute. What renders the Chava Falls discovery particularly compelling is the geological age of the rocks. The Bright Angel Formation is relatively young in geological terms, significantly younger than many of the ancient rock formations previously studied by Perseverance. An earlier hypothesis posited that indicators of ancient life would be predominantly confined to the most ancient rocks, formed during periods when Mars possessed a more substantial atmosphere and liquid water on its surface. The discovery of potential biosignatures in younger strata suggests that Mars might have retained habitable conditions for a more extended duration than previously conjectured, or that such conditions may have reappeared in later epochs. It is conceivable that periodic volcanic activity might have warmed the planet, melting subsurface ice and creating ephemeral oases where life could persist. The sample, officially designated Sapphire Canyon, in honor of a waterfall in the Grand Canyon, is now among 30 samples that Perseverance has meticulously collected and secured within sealed titanium tubes. These samples collectively represent a cross-section of Martian geology, comprising rocks from diverse eras and environments, each chosen for its potential to yield clues about Mars' past. The ultimate objective is to repatriate these samples to Earth through the Mars Sample Return mission, though this endeavour faces considerable technical and budgetary obstacles. The return of these samples would empower scientists to analyse them with instruments far surpassing the sophistication of anything currently deployable on Mars. Such instruments would facilitate measurements of isotopic ratios, facilitate the search for amino acids, and permit the examination of mineral structures at an atomic level. Until such time, the Sapphire Canyon sample resides within Perseverance's payload, a minuscule fragment of Mars holding what could be the most pivotal discovery in the annals of astrobiology, or conversely, something no more significant than an intriguing geological anomaly. The pervasive uncertainty is undoubtedly frustrating, yet it is also exhilarating. We are presently living through an epoch where the profound question of whether life exists beyond Earth may finally be answered, not through conjecture, but through direct empirical observation. Whether that definitive answer emanates from Mars, from the icy moons of Jupiter and Saturn, or from the spectroscopic analysis of exoplanetary atmospheres, the pursuit of knowledge is progressing at an unprecedented pace, fueled by technological advancements that were non-existent a mere generation ago. Some of these innovations, particularly within the realm of artificial intelligence, are evolving so rapidly that they are fundamentally reshaping multiple scientific disciplines. Chapter 7: The Silicon Mind. In 2024, the average corporation allocated $1.9 million towards generative artificial intelligence initiatives. Despite this significant investment, fewer than 30% of AI leaders reported satisfaction from their chief executive officers regarding the return on their investment. This discrepancy highlights a crucial aspect of our current position within the artificial intelligence revolution. The technology itself functions, at times with remarkable efficacy, yet translating this inherent capability into tangible business value has proven more challenging than the initial optimistic projection suggested. 2025 marks the year where this reality check is compelling a re-evaluation, compelling organizations to transition from exploratory experimentation towards focused and strategic deployment. This shift involves moving beyond the question of what can AI do, to the more pertinent inquiry of what problems can it genuinely solve more effectively than existing methodologies. The inherent capabilities of AI continue to advance at an astonishing rate. In September of 2025, researchers at Microsoft unveiled a groundbreaking achievement in protein simulation, leveraging an AI-driven system designated AI2OBMD. Proteins, often referred to as the molecular machinery of life, fold into intricate three-dimensional structures that dictate their specific functions. Understanding the intricate processes of protein folding and their subsequent interactions is paramount for advancing drug discovery, optimizing enzyme engineering, and elucidating the mechanisms of diseases. However, simulating protein dynamics has historically been a computationally intensive undertaking due to the large molecular size of proteins, which comprise thousands of atoms, and their behavior being governed by quantum mechanical interactions at the most fundamental levels. AI2OBMD empowers researchers to simulate these dynamics with an unparalleled combination of speed and precision, thereby potentially accelerating the discovery of novel pharmaceuticals and therapeutic interventions. This is not the sole domain where AI is revolutionizing scientific inquiry. Within neuroscience, a sophisticated AI model known as Cell Transformer, developed collaboratively by researchers at UCSF and the Allen Institute, has produced one of the most detailed anatomical maps of the mouse brain ever conceived. This groundbreaking map identifies 1,300 distinct regions and subregions, including previously uncharted areas. The model operates by meticulously analyzing vast spatial transcriptomic datasets, effectively mapping the expression of specific genes within individual cells and pinpointing their precise spatial locations. This analytical capability enables the AI to discern patterns and delineate boundaries that might elude human researchers, thereby revealing the brain's organizational architecture with a level of granularity that would require decades of manual effort to achieve. The identical AI methodologies can be applied to the analysis of other organs and tissues, including cancerous tumors, thereby unlocking new avenues for understanding disease progression and formulating effective treatments. Another significant AI breakthrough emerged from University College London, where researchers engineered an algorithm capable of distinguishing between different types of brain cells based on their electrical signatures with an impressive 95% accuracy. For decades, neuroscientists have been able to record the electrical activity emanating from neurons, but they have lacked the ability to definitively identify the specific type of neuron being observed without resorting to genetic markers or staining techniques. This novel approach harnesses AI to recognize subtle, distinctive patterns within the electrical spikes produced by various neuron classifications, effectively teaching a machine to interpret the neural code. The implications for the development of brain-computer interfaces and the treatment of neurological disorders such as epilepsy are profoundly significant. Nonetheless, as the researchers themselves caution, substantial progress is still required before this technology can be translated into a practical clinical tool. Beyond its role in accelerating research, AI is increasingly becoming integrated into everyday tools and operational workflows. Gartner predicts that in 2025, 75% of enterprises will transition from experimental AI pilot programs to full-scale operational implementation, necessitating a massive scaling of data infrastructure and analytical capabilities. AI agents, defined as autonomous or semi-autonomous software entities capable of perceiving their environment, making informed decisions and executing actions, are progressing from conceptualization to tangible reality. These are not the rudimentary chatbots of 5 years ago confined to pre-scripted responses. Instead, these are sophisticated systems empowered to manage complex tasks such as analyzing intricate legal contracts, orchestrating supply chain logistics, developing and debugging software code, and even providing personalized medical guidance. The emergence of AI agents engenders questions that extend beyond purely technological considerations. If an AI agent errs and causes harm, who bears the responsibility? Is it the developer who created it, the corporation that deployed it, or the user who placed reliance upon it? In late 2025, a lawsuit filed in Colorado brought these profound issues to the forefront when parents alleged that an AI chatbot had contributed to their teenager's suicide by engaging in simulated emotionally manipulative conversations. This case has the potential to establish a landmark precedent in determining liability for AI systems and defining the ethical obligations incumbent upon the companies that develop them. As AI capabilities expand and its integration deepens into sensitive domains such as mental health, education, and interpersonal relationships, society will be compelled to confront fundamental questions concerning trust, accountability, and the appropriate ethical boundaries for artificial intelligence. Furthermore, the question of how AI itself will evolve remains a critical point of consideration. Current large language models are trained on immense volumes of text data, meticulously scraped from the internet, thereby learning linguistic patterns that enable them to generate coherent and often useful responses. However, they lack a profound understanding of the information they process. They are deficient in common sense reasoning, prone to factual inaccuracies, susceptible to manipulation through adversarial inputs, and occasionally produce outputs that, while appearing confident, are entirely erroneous, a phenomenon known as hallucination. The subsequent generation of AI systems will need to address these inherent limitations, incorporating enhanced reasoning capabilities, the ability to self-verify their outputs, and perhaps a form of comprehension that transcends mere pattern matching. Some researchers posit that the path forward lies in the synergistic integration of diverse AI modalities, a concept termed composite AI. Rather than relying on a single monolithic large model, the approach involves constructing systems that amalgamate multiple specialized models, each proficient in a particular task, in conjunction with traditional software and databases. Others contend that a significant breakthrough will emerge from superior training methodologies or from a more profound integration of AI with robotics, thereby equipping it with a physical embodiment and sensory feedback mechanisms that enable it to learn about the physical world in a manner analogous to human cognition. Moreover, There is a burgeoning interest in neuromorphic computing, which involves the development of microchips designed to emulate the structural architecture of biological brains, potentially offering AI systems that are more efficient and capable than current paradigms. Regardless of the specific trajectory AI ultimately pursues, it is unequivocally apparent that we are still in the nascent stages of comprehending the full scope of this technology's capabilities and limitations, as well as its broader societal implications. The prevailing excitement is well-founded, and the potential benefits are substantial, yet the inherent challenges and risks are equally real. As we advance the development of increasingly powerful AI, it is imperative that we simultaneously cultivate the wisdom required for its responsible application. This same imperative for wisdom extends to another domain, where our fundamental understanding of reality may be undergoing a profound transformation: the enigmatic constituents that appear to comprise the vast majority of the universe. Chapter 8. The Illusion of Darkness. For approximately 100 years, cosmologists have operated under the premise that the universe is predominantly composed of substances that elude direct observation. Ordinary matter, the fundamental building block of stars, planets, and all living beings, constitutes a mere 5% of the universe's total mass energy content. An additional 27% is accounted for by dark matter, an invisible yet detectable entity discernible through its gravitational influence on galactic structures. The remaining 68% is attributed to dark energy, a force even more inscrutable, which appears to be driving the accelerated expansion of the universe. Collectively, dark matter and dark energy exert a dominant influence over the cosmic budget, shaping the very structure and ultimate fate of all existence. However, what if these concepts are entirely illusory? In October of 2025, a scholarly paper authored by Rajendra Gupta, an adjunct physics professor at the University of Ottawa, proposed a radical alternative hypothesis. Rather than populating the universe with imperceptible particles and unexplained energetic phenomena, Professor Gupta suggests that the fundamental forces governing nature, such as gravity, are undergoing a gradual diminution in strength as the universe ages. If this assertion holds true, then the observable phenomena we currently attribute to dark matter and dark energy might, in fact, be perceptual artifacts, consequences of applying immutable laws of physics to a universe where those laws are in a state of continuous, albeit slow, transition. This proposition is both remarkably simple and profoundly significant. We habitually assume that the gravitational force prevalent today is identical to that which existed 1 billion years ago and will remain so 1 billion years hence. But what if this assumption is fundamentally flawed? What if gravitational attraction was infinitesimally stronger in the past and will be imperceptibly weaker in the future? Such a temporal variation could account for the observed faster rotation of distant galaxies, a phenomenon that, based on visible matter alone, would be unexpected, thereby mimicking the effect attributed to dark matter. Furthermore, it could explain why the universe's expansion appears to accelerate over time, thereby imitating the influence of dark energy. Within this theoretical framework, there is no necessity for postulating exotic, invisible substances. Instead, the explanation relies upon time-varying constants, a universe where the governing rules evolve gradually as space itself undergoes expansion. This is not the inaugural instance of a proposal to modify our established laws of physics to obviate the need for dark matter and dark energy. Modified Newtonian dynamics, or MOND, has existed for decades and has demonstrated considerable success in elucidating the rotational curves of galaxies without invoking the presence of dark matter halos. Nevertheless, MOND has encountered difficulties in accounting for observations at larger cosmological scales, such as the behavior of galaxy clusters or the intricate patterns observed in the cosmic microwave background radiation, which is essentially the residual afterglow of the Big Bang. Professor Gupta's approach, which he terms CC plus TL, endeavours to provide a unified explanation that encompasses both the cosmological scale, where dark energy appears to exert its influence, and the astrophysical scale, where dark matter seems indispensable. By introducing a parameter that varies in accordance with both time and the local density of matter, he is able to accurately reproduce the observed rotational velocities of galaxies and the phenomenon of accelerated universal expansion, all without necessitating the introduction of any novel constituents. The timing of this theoretical proposal is noteworthy, as it coincides with other observational indicators suggesting that discrepancies may exist within our prevailing cosmological model. Data released in April of 2025 by the Dark Energy Spectroscopic Instrument, or DESI, indicates that dark energy might not in fact be a constant entity. Instead, it appears to be attenuating over time, evolving in ways that are not readily accommodated by the standard model. If dark energy is indeed subject to change, then our theoretical frameworks necessitate revision, and once such revisions are contemplated, it becomes prudent to question whether dark energy, as presently conceived, exists at all. Concurrently, experiments meticulously designed to detect dark matter particles have consistently yielded null results. The Lux-Zeppelin detector, recognized as the most sensitive dark matter detector ever constructed, has been operational for an extended period and has yet to register any conclusive findings. These investigations have established strict boundaries on the characteristics that hypothetical dark matter particles must possess, systematically eliminating vast expanses of theoretical potential. Each inconclusive finding renders the remaining possibilities for dark matter's identity more peculiar and less likely. Some researchers are beginning to question if we are pursuing something that simply does not exist, much like ancient astronomers who continuously added more intricate celestial circles to salvage the Earth-centered solar system model. However, discarding dark matter and dark energy is not straightforward, given their explanatory power. They account for galactic rotation patterns, the cohesion of galaxy clusters, the locations of gravitational lensing, and the specific arrangement of temperature variations in the cosmic microwave background radiation. Any novel theory must account for all these phenomena at least as effectively as the prevailing models, preferably with greater accuracy. Gupta's proposed model represents a step in this direction, yet it requires thorough validation against the entirety of cosmological data before it can be seriously considered a rival to the standard framework. The compelling nature of this scientific quandary stems from its engagement with the most fundamental inquiry in science. How do we ascertain reality? Dark matter and dark energy have eluded direct detection. Their existence is inferred from gravitational influences, the movement of observable matter, and the structure of space-time. Yet, inferences can be deceptive. For centuries, astronomers erroneously believed planets followed perfect circular paths, deeming circles the ultimate geometric form. The actual paths were ellipses, a more elegant solution once the preconception of perfection was abandoned. Could we be making a similar error now, assuming the universe comprises exotic substances when, in fact, our existing equations may need refinement? Future advancements and more comprehensive data will provide the answer. The Vera C. Rubin Observatory, slated to commence operations in late 2025 or early 2026, will undertake a sky survey utilizing the most powerful digital camera ever constructed, capturing images of billions of galaxies with unparalleled precision. The data gathered will scrutinize dark matter and dark energy models with a level of accuracy unattainable by current experimental setups. Similarly, the Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will measure the universe's expansion rate and chart the distribution of matter across cosmic scales. Between these new instruments and ongoing research, the upcoming years should elucidate whether dark matter and dark energy are actual entities, or if a fundamental re-evaluation of cosmology is necessary. Regardless of the outcome, this process reveals a beautiful aspect of scientific endeavour. It is an unending pursuit. Every resolution births new questions, and every established certainty eventually faces scrutiny. Occasionally, the most transformative discoveries arise not from finding something novel, but from realizing that our prior understanding was incomplete. Chapter 9: The Intervening Space. While scientists deliberate the cosmos's nature, and engineers develop quantum computers and fusion reactors, a quieter yet significant evolution is occurring in humanity's approach to venturing beyond Earth's atmosphere. On October 8, 2025, Blue Origin conducted its 15th suborbital tourism flight. The passengers experienced a brief period of weightlessness, observed the Earth's curvature against the stark blackness of space, and returned safely. For them, it was likely a life-altering event, evoking the profound perspective shift astronauts refer to as the overview effect. For the space industry, it represented routine business, another successful flight in an increasingly commonplace commercial operation. This increasing normalization of access to space takes on greater significance when viewed in a broader context. A generation prior, spaceflight was the exclusive domain of governmental agencies and highly trained professional astronauts who underwent years of rigorous preparation and selection. Now private enterprises are launching paying customers. While the cost remains exceptionally high for most, expenses are declining due to technological advancements and heightened competition. SpaceX has dramatically altered the launch landscape with its reusable rockets, substantially reducing the expense of orbital deployments. Blue Origin is similarly developing its own reusable systems. Other companies are engaged in designing spaceplanes, orbital hotels, lunar landers, and concepts for missions to Mars. The infrastructure being established today extends beyond mere tourism. It is constructing the foundation for a future where humankind becomes a multi-planetary species. SpaceX's Starship, the most massive and powerful rocket ever built, is engineered to transport cargo and eventually people to the Moon and Mars. NASA's Artemis program aims to return astronauts to the lunar surface, establishing a persistent presence and testing technologies essential for extended missions. China is constructing its own space station and has unveiled plans for a lunar base. India, Japan, and several European nations are progressing with their own spacefaring capabilities. This surge in activity prompts contemplation of our actions once we reach these destinations. Space is an unforgiving environment, devoid of air, lacking water, characterized by extreme temperature fluctuations, and subjected to solar and cosmic radiation. The creation of habitats capable of supporting human life will necessitate solutions in life support, agriculture, manufacturing, and medicine. Resource extraction from asteroids, the Moon, or Mars itself will be imperative, as transporting all necessary materials from Earth is impractical for long-term habitation. Energy sources will be required, likely solar power complemented by compact nuclear reactors. Furthermore, the psychological challenges of isolation, confinement, and distance from Earth must be addressed. However, perhaps the most crucial question is the fundamental justification for undertaking such endeavours. Pragmatic rationales include the potential for resource acquisition, scientific discovery, and ensuring humanity's long-term survival by establishing a presence beyond a single planet, vulnerable to existential threats like asteroid impacts or supervolcanoes. More idealistic motivations point to innate human curiosity and the inherent drive for exploration, the same impulse that led our ancestors out of Africa, across oceans, and spurs scientists to probe the deepest mysteries of nature. Space represents the ultimate frontier, not due to its emptiness, but because of its vastness, its largely uncharted territories, and its boundless potential that we can barely conceive. Crucially, space exploration is not isolated from the scientific and technological advancements discussed. Quantum computers may one day optimize spacecraft trajectories or enable novel forms of communication across vast interplanetary distances. Fusion reactors could provide the power necessary for rapid propulsion systems, reducing transit times to Mars from months to mere weeks. Artificial intelligence will be indispensable for managing the complexity of life support systems, autonomous navigation, and analysing the immense volumes of data collected by sensors. The ongoing search for biosignatures on Mars or the moons of Jupiter informs our understanding of where and how to seek extraterrestrial life. Everything is interconnected. The universe is not a collection of disparate elements, but a tapestry of relationships, with patterns repeating across various scales and principles, applicable across different domains. A comet's chemical composition offers insights into planetary formation. The behavior of a quantum computer reveals fundamental truths about reality. A fusion reactor emulates processes occurring within stars. An AI system mapping brain activity illustrates how complexity emerges from simple rules. And a private spaceflight company incrementally expands the possibility of humans becoming denizens of the solar system, rather than confined to a single planet. These interconnections are significant as they underscore that progress is not a linear progression, confined to isolated fields. Instead, it arises from cross-pollination, where concepts developed in one area find unexpected utility in another, and through collaborative efforts of individuals from diverse disciplines tackling problems too complex for any single perspective to solve. The groundbreaking achievements of 2025 in quantum computing, fusion energy, Mars exploration, AI, cosmology, neuroscience, and space access are not isolated narratives. They are chapters within a grander chronicle of human ingenuity and inquisitiveness. Chapter 10. The Horizon. We commenced our journey with an asteroid that passed unnoticed and a comet illuminating the October sky, both serving as reminders of the universe's dynamic nature and our simultaneously infinitesimal yet significant place within it. We observed a distant planet forming moons from a disk of gas and dust, a process mirroring the birth of our own moon billions of years ago. We witnessed quantum computers attaining a level of sophistication that may soon unlock solutions beyond the capabilities of classical computing, and fusion reactors sustaining plasma for durations that hint at a future powered by the very reactions that ignite stars. We examined a rock on Mars that could potentially harbour evidence of past extraterrestrial life, though this question remains open and likely will persist until such samples can be analysed in terrestrial laboratories. We observed artificial intelligence mapping brains, simulating proteins, and raising novel questions regarding autonomy, accountability, and the very definition of intelligence. We contemplated theories suggesting that dark matter and dark energy, the unseen components believed to dominate the cosmos, might not exist. This implies that our current understanding of the universe might be founded upon incomplete equations. Furthermore, we noted the quiet, incremental progression towards greater accessibility in space travel, moving from a niche activity towards a more widespread, albeit still costly, undertaking. Each of these developments carries inherent uncertainty. Quantum computers may encounter unforeseen obstacles that postpone their practical deployment. The commercialization of fusion reactors might prove more challenging than optimists anticipate. Martian biosignatures could ultimately prove to be geological rather than biological in origin. AI development might reach a plateau, or require conceptual breakthroughs yet to be imagined. Alternative cosmological models may fall short of explaining observations as comprehensively as dark matter and dark energy, and space exploration might remain prohibitively expensive and perilous, accessible primarily to governments and the ultra-wealthy. However, uncertainty does not equate to futility. It is the fertile ground where discovery blossoms, understanding expands, and ideas are tested against reality, undergoing revision when they prove inadequate. Science is not a static collection of facts, but a dynamic process of inquiry and refinement. The questions we pose today are among the most profound ever articulated. What constitutes the universe? How did life originate? Can we harness stellar power? What is consciousness? Are we alone? How do we ensure that our creations serve humanity's benefit rather than its detriment? These profound inquiries do not possess simple answers, and that is precisely their value. Their complexity makes them worthy of pursuit, yielding knowledge, inspiring technological innovation, and profoundly shifting our perspectives as our understanding deepens. A century ago, we were unaware of the universe's expansion. 50 years ago, we had not deployed rovers on Mars or detected exoplanets. 25 years ago, quantum computers were mere laboratory curiosities, and AI struggled to recognize handwritten digits. The pace of advancement is accelerating, fueled by cumulative progress in computing, materials science, instrumentation, and fundamental knowledge. What will the next decade unveil? If fusion energy achieves commercial viability, an abundance of clean power could revolutionize civilization, alleviating poverty for billions and enabling projects currently considered infeasible. Maturation of quantum computers could accelerate breakthroughs in drug discovery, materials science and cryptography, reshaping industries and global dynamics. Confirmation of biosignatures on Mars or detection of life's markers on an exoplanet would represent one of humanity's most significant discoveries, proving that life is not unique to Earth. Continued AI advancement could foster a partnership in scientific research, generating hypotheses, designing experiments, and analyzing data on scales surpassing human capacity. And if space access continues to democratize, the resources and knowledge of the solar system could become a shared heritage, accessible to future generations in ways we can only begin to envision. Yet, these potential advancements are accompanied by inherent risks. Technologies are tools, capable of being wielded for beneficial or detrimental purposes. Quantum computers could compromise the encryption protecting sensitive financial and military communications. Fusion technology, if weaponized, could unleash unparalleled devastation. AI could perpetuate existing biases, displace human labor, or be employed in ways that diminish rather than enhance human well-being. Reckless pursuit of space exploration could result in planetary contamination, destruction of irreplaceable scientific sites, or exacerbation of existing inequalities. Navigating these risks demands more than technical expertise. It requires wisdom, ethical consideration, foresight, and a willingness to contemplate not only what is possible, but also what is right. It necessitates the inclusion of diverse voices in decision-making, transparency regarding risks and uncertainties, and humility regarding the limits of our comprehension. The scientists and engineers pushing the frontiers of knowledge are acutely aware of these responsibilities, even if public discourse often polarizes technology as either a panacea or a threat, neglecting the nuanced middle ground. The reality is more intricate. Technology is neither inherently good nor bad. It amplifies human intentions and capabilities. In capable hands, pursuing noble objectives, it can resolve challenges, alleviate suffering, and expand human potential. In misguided hands or with myopic goals, it can inflict harm. The imperative is to cultivate systems, institutions, and cultures that steer towards the former and away from the latter, a responsibility that extends to all of us, not solely to scientists and policymakers. Thus, here we stand in October of 2025, observing comets brighten, delving into quantum entanglement, learning of plasma record-breaking achievements and potential biosignatures. The cosmos continues its ancient majestic ballet. Stars are born and perish, galaxies collide, comets hurtle towards the sun, and moons coalesce from nascent dusty disks. Life, at least on this solitary blue world, has learned to gaze outward, to pose questions, to devise tools that extend our senses and comprehension, and to envision futures where the boundaries of the possible recede into the unimaginable. Thank you for joining me on this exploration of recent discoveries and breakthroughs. If you found this journey insightful, please consider leaving a like and subscribing to remain connected as science continues to unveil the universe's secrets. The endeavour to understand our cosmos is ceaseless, and each answer we uncover reveals new mysteries beckoning just beyond the horizon. As always, all information presented herein is for educational purposes, grounded in current research and understanding, which is in perpetual evolution. Continue to look upwards, persist in asking questions, and remember that we are all integral parts of this grand unfolding narrative. Until our next encounter, wherever you're listening from, whatever the hour, good night.